Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. This week in astronomy, Hubble crisis, right-handed neutrinos and water from first stars. The Hubble crisis, rethinking the universe's expansion. The universe appears to be expanding at a rate faster than what theoretical models predict, challenging our current understanding of physics. This discrepancy, known as the Hubble tension, has been the subject of intense debate. Now, new results published in the astrophysical journal Letters reinforce the evidence for this faster rate of expansion, pushing the tension to what researchers are calling a crisis in cosmology. The expansion rate of the universe, called the Hubble constant, has been a focus of scientific investigation since Edwin Hubble's groundbreaking discovery in 1929 that the universe is expanding. Dan Skalnick, a physicist at Duke University, likens this pursuit to constructing the universe's growth chart. While we understand the universe's size at the time of the Big Bang, there is still uncertainty about how it has grown to its current size. The distant universe, representing the universe's baby picture, and the local universe, akin to its current headshot, do not align when connected using the standard model of cosmology. This mismatch suggests that the widely accepted model of the universe may be flawed. To refine measurements of the Hubble constant, researchers rely on a cosmic distance ladder, a stepwise method for measuring distances to celestial objects. Each rung on this ladder depends on the calibration of the previous one. A crucial breakthrough came when Skalnick used data from the Dark Energy Spectroscopic Instrument, DESI, which observes over 100,000 galaxies nightly, to anchor the ladder closer to Earth. The key to this improvement was obtaining a precise distance to the Coma cluster, a nearby galaxy cluster. Skalnick and his team used the light curves of 12 Type Ia supernovae within the cluster. These supernovae, often referred to as standard candles, have a predictable luminosity, making them reliable for measuring distances. Their calculations placed the Coma cluster at approximately 320 million light-years away, aligning with a range of distances reported over decades, reinforcing confidence in the result. Using this refined distance as the foundation, the team recalibrated the cosmic distance ladder and determined a Hubble constant value of 76.5 kilometers per second per megaparsec. This value indicates that the universe expands by 76.5 kilometers per second for every 3.26 million light-years of distance. While this measurement matches other recent observations of the local universe's expansion, it conflicts with predictions based on the distant universe and the standard cosmological model. This divergence raises a critical question: is the problem with the measurements themselves or with the underlying theoretical models? According to Skalnick, the growing evidence points to the models being the issue. Over the years, numerous reanalyses have been conducted, and despite changing methodologies, researchers consistently arrive at similar values for the Hubble constant. This consistency strongly supports the idea that the tension originates from a flaw in the models rather than the measurements. The implications of this work are profound. The findings suggest that the cosmological models developed over the past 25 years may need significant revision. Skalnick emphasizes that these results are pushing the boundaries of our understanding, signaling that there are still unknowns in the field of cosmology. This ongoing exploration may fundamentally reshape our understanding of the universe and open the door to new discoveries about its nature and origins. Right-handed neutrinos, unlocking cosmic mysteries. New research suggests that strange particles known as right-handed neutrinos may hold the key to understanding why the universe is filled with matter instead of nothing, offering potential explanations for several long-standing mysteries in physics. In the realm of fundamental interactions, most processes are symmetrical, producing equal amounts of matter and antimatter. Yet, our universe contains primarily matter, with antimatter only appearing in rare, high-energy events. This imbalance has puzzled scientists for decades, and right-handed neutrinos might provide the answer. Neutrinos themselves are enigmatic particles. They exist in 3 types, or flavors, and have extremely small masses. Unlike other particles, all known neutrinos are left-handed, meaning their internal spins align in a specific direction as they move. This unique behavior sets them apart from other particles, which can have spins oriented in both directions. Physicists, however, suspect the existence of undiscovered right-handed neutrinos, which would be much heavier than their left-handed counterparts. In the early universe, when temperatures were incredibly high, both types of neutrinos could have interacted freely. As the universe expanded and cooled, a critical event, symmetry breaking, would have caused the heavy right-handed neutrinos to become invisible to detection. This symmetry breaking might have separated matter from antimatter, resolving the imbalance that left the universe dominated by matter. The story of right-handed neutrinos doesn't end there. Researchers propose that these particles may have given rise to a new entity called the majoran. This hypothetical particle would be its own antiparticle and could still exist in the universe today as a relic from the early cosmos. Importantly, the majoran might fit the description of dark matter, the elusive substance that makes up most of the mass in galaxies but has never been directly observed. If true, this hypothesis connects 3 major puzzles: why all known neutrinos are left-handed, why the universe contains more matter than antimatter, and what constitutes dark matter. While this idea remains theoretical, it offers an exciting avenue for further research. Discovering evidence for right-handed neutrinos would not only reshape our understanding of neutrinos but also help unravel the fundamental mechanisms shaping the universe's evolution. Such a breakthrough could bring us closer to solving some of the deepest mysteries in cosmology. Water from the first stars, a cosmic legacy. Water is fundamental to life, and every living organism on Earth contains it. Earth's abundance of life is intrinsically tied to its abundance of water, a relationship stemming from water's remarkable properties and its widespread presence in the universe. Composed of 2 hydrogen atoms bonded to 1 oxygen atom, water's structure is both simple and robust. Hydrogen, the most abundant element in the cosmos, originated in the fiery aftermath of the Big Bang, while oxygen is produced in the nuclear furnaces of massive stars through the carbon-nitrogen-oxygen (CNO) fusion cycle. Given this origin, scientists have generally believed that oxygen, and, consequently, water, became more abundant over cosmic time. As generations of stars lived and died, they cast oxygen into space, enriching the universe with the ingredients for water. This progression implies that water was scarce in the early universe but became common in later epochs. However, a new study challenges this assumption by suggesting that water may have been more abundant earlier than previously thought. Astronomers classify stars into populations based on their age and chemical composition. The youngest and most metal-rich stars, like the Sun, are categorized as population 1. Older stars with fewer heavy elements are population 2. The oldest stars, the first to form after the Big Bang, are known as population 3. These population 3 stars, consisting solely of hydrogen and helium, were massive and short-lived. Though they have not been directly observed, they played a pivotal role in shaping the universe, producing the first heavy elements, and, potentially, the first water. The recent study modeled the explosive deaths of early stars, focusing on both massive, 200 solar masses, and smaller, 13 solar masses, stars. The massive population 3 stars likely formed directly from primordial hydrogen-helium clouds, while the smaller stars emerged in early stellar nurseries with very low metallicity. Upon their deaths, the smaller stars exploded as typical supernovae, while the massive stars underwent parent stability supernovae, extremely energetic explosions unique to their size. Simulations suggest that these early stellar deaths significantly enriched their surrounding environments with water. The molecular clouds formed from their remnants contain water fractions 10 to 30 times greater than those in diffuse molecular clouds within the Milky Way today. This enrichment implies that by 100 to 200 million years after the Big Bang, there may have been sufficient water in molecular clouds to potentially support the development of life. However, whether life emerged so early in the universe remains an open question. While water formed in significant amounts during this period, subsequent ionization and other astrophysical processes may have destroyed many of these molecules. The universe likely entered a dry phase before later generations of stars, population II and I, replenished water levels. Nevertheless, the study suggests that much of the water present in the universe today may trace its origins back to the first stars, making them a foundational source of this life-sustaining molecule. This insight reshapes our understanding of water's cosmic history and its role in the potential emergence of life.